Good evening, everybody. Welcome to the Irish Astronomical Association's 6th Zoom meeting of this 2020-2021 session. I'll start by introducing myself. I'm Danny Collins. I'm the current honorary pres of the association. We have a few opening bits of news and reminders of what's coming up, if bear with me. Two news items from the last day or so. One interesting one sad one. You probably guess what they are. The interesting one is the Chang'e 5 landing, the Chinese sample recovery probe, landed near Mons Rumker in Oceanus Procellarum on the moon. It'll be interesting to see if everything goes to plan there. And also, it looks it's very reminiscent of the Apollo missions architecture, in that they have the lander, which consists of two parts, and only the top part takes off again. And RVs with the mission, the support mission part of the probe before heading back to Earth. The sad thing, of course, is the Arecibo Observatory radio telescope collapse, when the 900-ton instrument package basically broke the three towers and just fell in a big heap. Very sad indeed. Forthcoming events for the month, the three main ones are the Geminids, which will be active between the 4th and the 17th of December. The peak is estimated to be around the 14th. Then the Ursids, which are not as well known, between the 17th and 26th December. They will peak on the nights of the 21st, 22nd and the 22nd, 23rd. But of course, the biggie, the great biggie, is a great conjunction on the 21st, when Jupiter and Saturn come just 6.1 arc minutes apart. Considering the moon is 30 arc minutes in diameter, it will be a glorious sight. Our webmaster Paul has put a screen grab from Stellarium up on the front page of our website. You can have a look at it there. And of course, if you have Stellarium, you can play around with it and watch the thing coming on that date. Just put the 21st December into the time and date box. One other little thing, the Comet Erasmus, 2 or 3 weeks ago, was picked up. Very difficult object, low down on the horizon just after dawn, just before dawn, 6 a.m. or so. But very little time before it disappeared into the rising daylight. I got up a couple of mornings around 6, but no joy at all, beaten by the clouds. So have to look forward to the next, hopefully bright comet at some stage. With regard to the main part of our talk with our guest speaker, if you have any questions, as before, could I ask that you just use the chat button at the bottom, type in your questions, and at the end of the talk, then we can pull the questions out and get you to expand on them if you wish. Now to our guest speaker, Dr. Caitriona Jackman, and I'll just go over her background. She is honorary professor at the DIAS, the Dublin Institute for Advanced Studies, where she leads a research group on planetary magnetospheres. She's worked with data from missions, including NASA's Cassini at Saturn, ESA's cluster mission in orbit around Earth, NASA's Juno at Jupiter, and with data from the Hubble Space Telescope, and the Chandra X-ray Observatory. Her research interests include understanding how the aurora works and how machine learning and complexity science can be used to study huge volumes of data from space. So, having done that, Caitriona, it's over to you.
Super, thank you, Danny. Let me share my screen. Okay, everybody seeing the solar system from my screen, I hope?
Yes.
If not, shout very loudly. Okay, great. Right, it's lovely to be with you all. Sorry that I'm not there in person to avail of the tea and biscuits, but I shall find some in my kitchen after I'm finished chatting to you. I love planets. I love magnetized planets in particular, and my research centers around planetary magnetospheres, and has been dominated in the past 17 years by the study of the planet Saturn and more recently the planet Jupiter, with a bit of Mercury and Earth thrown in there for good measure. And also I've been interested in looking a little bit as well at the ice giants Uranus and Neptune. But this figure, which I'm showing you here, just gives you a hint of the beauty and diversity that there is in the solar system, with the 4 rocky terrestrial planets. And let me make my pointer shiny. The 4 rocky terrestrial planets, then the 2 gas giants, which I'm going to focus on in detail tonight, and then the ice giants. And Pluto was lost to us as a planet in 2006, but still very much there and still very much an interesting object. Okay, so what I'm going to do tonight is talk primarily about Jupiter and Saturn. And I always start with Saturn, even though it's further from the sun than Jupiter. And that's just my own personal biases, because my career started with Saturn when I was an undergrad in Limerick. I did a work placement at the Mullard Space Science Lab, where I worked with data from the Cassini spacecraft, which at the time was on its way to Saturn, and then had the absolute privilege of working on the Cassini mission for more than 15 years. So Saturn is very dear to my heart, and always the first planet that I come to. So in terms of history of observation, of course, if we were all in the room together, I'd ask for a show of hands of how many of you have seen Saturn in the night sky, and I would imagine it's most or all of you. It's a very beautiful object to observe in the night sky, and one which changes throughout its seasons in terms of the tilt of its rings relative to the observer. And so that gives you some very different views. And when we look back at early astronomers, way back to the 1600s, the likes of Galileo and Cassini-Huygens and Cassini, we can see now what they were sketching, but at the time it was confusing to them. So Galileo in 1610 was looking at Saturn and thought maybe there was, a central orb with 2 perhaps bright stars either side. And then as the seasons evolved, he thought, oh, maybe there's some kind of a strange elliptical shape with these sort of dark triangles, which of course we now can think, well, that was just the rings tilted towards the observer. Then as telescopes became more sophisticated and knowledge grew, Cassini-Huygens came to the conclusion that Saturn was surrounded by a solid ring. And then moving further on, Cassini said, actually, it looks like there might be a gap between the main rings, and that is the gap which we now call the Cassini division. So fast forward to the late 70s and early 80s, and that was our first chance to get a close-up glimpse of Saturn with spacecraft. So the Pioneer and Voyager spacecraft flew by, and their trajectories are shown here: Pioneer in red, Voyager 1 in green, and Voyager 2 in blue. So the sun off to the right of this diagram and Saturn here at the center. And you can see they just sort of flew towards Saturn, did a quick spin around the planet, and then they were on their way elsewhere. And of course, we now know the Voyagers are exploring interplanetary space. So they just gave us a flavor of what could be seen at the Saturn system. And it was really Cassini that completely changed our view of Saturn, its rings, its moons, and its atmosphere. And this figure shows the trajectory of the Cassini mission from 2004 to 2015. It actually finished in 2017. And it's just like a ball of wool, just so many different strands, different trajectories, taking the spacecraft to lots of different vantage points. And that was to fulfill the many and diverse scientific aims of the mission. So to go close to the planet and look at its atmosphere and measure its magnetic field to a high degree of resolution, then to go further from the planet and look at particular moons or have high latitude views down onto the northern and southern poles, for example, to study the aurora. So each of these different trajectories had a very distinct scientific purpose. And so, just a little bit of history of Cassini itself. Here it was in the going through its sort of vibration and thermal testing. And here's a space agency operative for scale. So it's about the size of a double-decker bus. Here it is on the launch pad, and here it is on its way to Saturn. Because Saturn is very, very far away, it's impractical to take a direct flight from the Earth to Saturn. So it was launched in 1997. And then it had a couple of swing-bys where it used the gravity of other planets in the solar system as a kind of a slingshot to give it a boost and send it on its way. So it had an Earth swing-by and 2 Venus swing-bys. And then the Millennium flyby of Jupiter, followed by Saturn orbit insertion in July of 2004. And an amazing arrival at Saturn where the spacecraft used the high gain antenna, which is this white thing, which is like a giant umbrella, to kind of shield it as it passed directly up through the rings, and then was captured into a stable orbit around the planet Saturn. And the instrument that I worked primarily with was the magnetometer, which was actually a dual technique instrument, which is on this really long boom sticking out of the spacecraft. And the length of the boom is there to keep the magnetometry as far away as possible from any stray electronic disturbance from the main body of the spacecraft. This is kind of a spoiler alert for the rest of the talk, but just some, highlights of the Cassini mission include, the moon Enceladus, which I'm going to talk about it in a bit more detail. This beautiful icy moon, which turned out to be one of the biggest surprises of the mission. The landing of the Huygens probe on the moon Titan. So Huygens is this kind of barbecue-shaped gold thing that was stuck onto the side of the spacecraft and then was released. I think it was on Christmas Day in 2004, and then landed on the surface of Titan in January 2005. And it still amazes me to think that we've successfully landed on a moon so far away in the outer solar system. A real technical challenge. And then fantastic and more than just beautiful, but intriguing images of Saturn's atmosphere, such as this one, which illustrates the polar hexagon, which is this persistent atmospheric cloud structure, which we see above Saturn's poles. It's just sort of some of the highlights from Cassini. Just going to hop to Jupiter now and take the same kind of framework here. So consider that the history of observation of the planet Jupiter. So again, I'm sure you've all seen Jupiter in the night sky, whether you know it or not. But looking at Jupiter and looking at the Galilean moons, so the 4 moons, Io, Europa, Ganymede, and Callisto, it's just a great beginner's intro to astronomy and planetary science because they change effectively nightly, and that's illustrated quite nicely here by some of these original drawings by a very famous old astronomer who I'm sure many of you know who it was. There might be a prize at the end if you can guess. Okay, there won't be a prize, but anyway. These are drawings which show Jupiter at the center and then the position of the Galilean satellites shown by these asterisks.
Your dad? All right, tell him to ignore
either side. Can you still hear me? I assume you can. Either side of the planet, and you can see that they are, moving relative to each other and appearing on different sides of Jupiter on successive nights. So again, while you get a nice and an interesting view of Jupiter from here on Earth, of course, when you have the capability to go there with spacecraft, that's what you want to do. And so while we've had 3 flybys and an orbiter at Saturn, we've had many, many more flybys of Jupiter. And that's partly because Jupiter is a really interesting place to go, but it's also because Jupiter is the biggest planet in our solar system and is a really great planet to give you a significant boost if you're trying to go somewhere else. So to be a great site for gravity assist. And so this figure again shows, similar to the already showed you, it shows the trajectory of different spacecraft that have been to Jupiter. So the sun off to the right, and you'll recognize some of the names. So, Voyager 1, Pioneer 11, Voyager 2, Pioneer 10, and they were all on their way elsewhere. In green, we've got the trajectory of the Ulysses spacecraft, which did effectively a handbrake turn, not a technical orbital mechanics phrase, but a handbrake turn at Jupiter to crank its latitude up and actually get it over the poles of the sun. And then we had New Horizons going all the way down the magneted tail of Jupiter. I'll come back to that later on its way to Pluto, and then Cassini in blue on its way to Saturn. The black shows the orbit of the Galileo spacecraft, so the first spacecraft to go into orbit around Jupiter. But everything has changed at Jupiter in the past couple of years with the arrival of Juno. So Juno is a NASA mission to Jupiter, and one of the most ambitious spacecraft and one of the most ambitious trajectories for a spacecraft. Here's a artist impression of the trajectory, which takes the spacecraft really, really close to the planet near the equatorial plane. So getting a fantastic close-up view of Jupiter's cloud tops and Jupiter's atmosphere. And then when it's getting over the poles, it's threading right through these magnetic field lines and looking right down onto the northern and southern auroral regions. And actually, one of the key science questions of the Juno mission is, how does the polar magnetosphere work? So how does this region near the north and south pole, all these magnetic field lines, have their origin? What is the physics of the magnetic field and plasma in that region, and how does that lead to the generation of the aurora? And that's core to my research and the research of my group. But getting so close to Jupiter is risky because you've got the radiation belts of Jupiter, which are really, really intense and very unfriendly for spacecraft electronics. Another one of the big questions of Juno is, what is inside Jupiter? And it sounds like a cliche to say, you know, we're rewriting the textbooks on Jupiter, but actually we are, because we don't have a good sense of what is inside the planet. And that's so critical for our understanding of just how the solar system itself formed. And so these figures illustrate how the trajectory will completely encase the planet over the course of the entire mission. And so we'll sample every latitude and longitude in this complete sort of orbital net. And the scientific significance of that is that for people who use magnetometry, who are using Juno's magnetic field sensing instrument, that will enable them to get incredibly high resolution views of the interior magnetic field of Jupiter, to understand more about the dynamo action that goes on inside, and ultimately to decipher what's going on in the core. And you know, I struggled to pick just one image from Juno of Jupiter's atmosphere, but many of you may know that Juno has a public engagement and outreach instrument on board called JunoCam. It's not really a science instrument. It's there to take amazing pictures, but also to give the public a chance to decide where it points, but also to download those raw images and do whatever kind of processing they want to do. And that has resulted in some, frankly, spectacular imagery of the complexity of things like the Great Red Spot and these sort of swirls and vortices of Jupiter's incredibly turbulent atmosphere, and that's a real strength of the mission. So again, some highlights for Jupiter, a bit of a spoiler for things that I'll go into detail on in a few moments, but Jupiter's aurora, you know, is central to my interests. But Jupiter is a planet of superlatives. It's the biggest planet in the solar system. It's got the strongest magnetic field. It's also got by far the most powerful auroral emissions in our solar system. Here are shown in ultraviolet, but it also has emissions in X-ray wavelengths and also in infrared. It has very intense radiation belts, which I also already mentioned, which are very inhospitable for spacecraft you're trying to orbit through them. And it's got some amazing moons. I'll talk about Io in a bit, but it's also got a moon called Europa, which is going to be the primary focus of an upcoming NASA mission called Europa Clipper. And it's sort of from the realms of sci-fi almost, because Europa is now believed to have a significant subsurface liquid ocean beneath an icy crust. And you know, anywhere where you think liquid ocean, immediately one's mind goes towards maybe that is linked to conditions for life, or somewhere which now or in the past was a habitable environment. So Europa is a really interesting astrobiology target. Okay, and then spacecraft coverage. Here's a figure with labels that are relevant for Jupiter, and the bottom has labels that are relevant for Saturn. So it's a sunspot number as a function of time from 1970 to 2020. And so this is showing what's called the solar cycle. So sunspots are just these intense regions of magnetic field on the sun, and they wax and wane from minimum to maximum over an 11-year cycle. And that solar activity has implications for the entire solar system, particularly if you're interested in magnetic fields and plasmas and charged particles. But this figure just gives us an idea of the coverage that we've had at these planets. So at Jupiter, for the top panel labels, we've had Pioneer 10, 11, Voyager 1 and 2, Ulysses a couple of times, Cassini, New Horizons, and then orbiters, we've had Galileo and now Juno. And at Saturn, labels on the bottom, we've had Pioneer, Voyager 1 and Voyager 2, all in quite close succession, and then nothing for ages, and then Cassini being amazing for 13 years. So we have coverage at both planets at all stages of the solar cycle. And crucially, for a mission like Cassini, we have coverage at all planetary seasons. And that's really important if you're wanting to understand things like asymmetries between northern and southern hemispheres, and what happens if you're facing the sun for a long time and then in the dark for a long time. What does that do to the dynamics of a planet? And so it's really important to have that kind of broad range of coverage. Okay, so I wanted to just focus on a couple of highlights that I but one I wanted to flag, Enceladus, of course. Amazing discovery about Enceladus from the Cassini spacecraft. So Enceladus is one of Saturn's icy moons. Saturn has many, many moons, and many of them are icy. It wasn't particularly expected to be anything special pre-Cassini, but it is something very special indeed now. So you can see straight away by looking at this image of Enceladus that the north and south are very different. So the north is very heavily cratered, whereas close to the South Pole has these long fractures, which we actually call tiger stripes, running all along near the southern polar region, and also quite fresh, clean ice as opposed to craters. Now, what's making fresh, clean ice? Well, we'll see in a second. So the first time that Cassini flew by Enceladus, way back in 2005, and indeed the second time, we weren't expecting to see anything with the magnetometer instrument other than just Saturn's magnetic field, because Enceladus is orbiting close to the planet Saturn. Here are these labeled with these arrows are Saturn's magnetic field lines, like a dipole. And if Enceladus is just an inert, unmagnetized or inactive icy moon, you wouldn't expect any change in magnetic field. But the magnetometer registered a residual change in the magnetic field. So an indication that the field was somehow being bent around the moon. So maybe that the plasma was being slowed in the location of Enceladus. And this was really puzzling, and puzzling enough that actually my old boss at Imperial College, Michelle Doherty, Professor Michelle Doherty, FRS, went to the mission planners at NASA and said, "This is a really strange signal. We were not expecting this. Can you take us a bit closer?" And mission planners are nervous to do an orbit burn and change the trajectory, but this was too good a chance to miss. And so they went closer. They went about 173 kilometers for the flyby in July of that year, and then we really cracked it and identified that this bending of the field was due to outgassing from Enceladus via a plume from the pole. And actually, the temperature maps show that the temperature was much, much hotter at the South Pole than it was anywhere else. Now, that's all relative because it's just generally a pretty cold place, but it's, minus 201 everywhere else. And then along these tiger stripes, it's minus 93. And there are specific jets associated with plumes, like geysers, like you would see in Iceland, coming out of these tiger stripes. And over the years, with more flybys of Enceladus and a combination of observation and scientific modeling, we've been able to really quantify the dynamics of this system. So we've been able to measure how much material is coming off. So it's about 100 kilograms a second. What's in the plumes? Well, it's water ice. What happens to that material when it comes off? Well, it forms a brand new ring all the way around Saturn called the E ring. And we're even able to observe sort of temporal change, so the expansion and contraction of those fissures as Enceladus moves around Saturn. And towards the end of the mission, there was a very exciting report of the detection of hydrogen from these plumes. And this fits into this magic angle of, what are the ingredients for life? Well, liquid water, an energy source, and certain chemical compounds. And over time, those things combining can give you life. And so whenever we see certain chemical composition, and we know that there is evidence of an energy source which is producing these geysers and liquid water, that's a pretty heady combination. And I should say, very clearly that the claim is not that life has been detected on Enceladus, but that it is a place which may now or in the past have had the conditions which could support life. So this is just one picture showing you here on the right. One idea could be this icy shell with a subsurface ocean and some kind of interaction happening at hydrothermal vents at the bottom of this ocean. That's a possibility. Of course, we want to go back, and when we go back, we go with more specifically optimized instrumentation to look at this exact question. Okay, one moon of Saturn. Now I'm going to talk about one moon of Jupiter. So Io is another fascinating moon. It's not as pretty as Enceladus. It looks a bit like the color of snot. That's because it's one of the most volcanic bodies in the solar system. But it's critical to understanding particularly the dynamics of Jupiter's magnetosphere, because it is the source of so much material that becomes ionized or charged, and it feeds Jupiter's magnetosphere with a huge amount of plasma. And in a second, I'm going to show you the consequences of that. But why is Io as it is? Well, it's because of its specific location in its orbit around Jupiter. So that's sort of illustrated here. We've got Jupiter, of course, at the center, and then the Galilean satellites in orbit around Jupiter. So you've got Io, and then you've got Europa and Ganymede, and indeed Callisto further out. And they're in a particular type of orbital resonance, so that there are times when Jupiter is exerting a certain force, pulling Io in one direction, and then Europa and Ganymede are lined up on the other side of Io, pulling it in the other direction. And so this kind of push-pull action from side to side has the effect to produce something called tidal heating at Io. And this leads to enormous volcanoes. And if we look at some of these images, which I'm showing you on the bottom, on the left are images from the Galileo spacecraft. And you can see a volcano which has been called Prometheus, erupting there to a height of about 60 kilometers. And then, more than 20 years later, almost 20 years later, is an image from the New Horizons spacecraft. And again, Prometheus is still going, but there are other volcanoes which are active at this time. This one, Tvashtar, is erupting to a height of about 290 kilometers. And this one here, Masubi, is erupting, but it's in shadow, but it's just that it's erupting so high that the top of its plume is just caught by so there's a lot of volcanism going on at Io, and as I say, it's an important source of plasma or charged particles. And so what actually happens is Io here is orbiting around Jupiter. It's emitting all of these particles initially as neutrals, and then they become ionized. And they form a plasma torus, which is just a fancy word for like a donut of plasma around the planet. And that can lead to interactions between the magnetic field and the plasma, which result in electrical currents being produced. And they can directly travel along magnetic field lines into the auroral zones, north and south. And the observational consequence of that is that Jupiter's ultraviolet aurora has a little footprint and a tail, which is directly related to the moon Io. In fact, there are also footprints associated with Ganymede and Europa, but they're much, much fainter. So Io literally, makes its mark on Jupiter and on Jupiter's magnetosphere and aurora. Okay, so I couldn't not talk about magnetospheres. So let me play the movie. So this is, oopsies, keep playing. There we go. This is how magnetospheres form. So we start with the sun, which itself is a giant magnet and is the source of the solar wind, which is a flow of plasma or charged particles, which is constantly flowing away from the sun at speeds of about 500 kilometers per second on average. When the solar wind encounters the obstacle of a magnetized planet like the Earth or Jupiter or Saturn, much of that flow is deflected around the planet, but there can be interaction between that field and plasma. And I'm going to show you a static image of that here on the top right. So we see the sun here hitting the solar wind and the coronal mass ejection at the same time. And here is, in this case, it's Earth's magnetosphere, but we see much of this flow being deflected around. And then, of course, what is providing this obstacle is the planet's magnetic field itself. So here, for the case of the Earth, we see this cutaway. We can see the interior of the planet and these invisible field lines extending large distances from the planet, and they're shown here in yellow. And so you can think of a planet's magnetic field like a giant shield or sort of an umbrella that's holding off and protecting us from this solar wind flow, but is also being very much shaped by the solar wind flow. So a bit squashed in on what we call the day side, which is the side facing the sun, and on the night side stretched out into a very long tail, which we call a magnetotail. Now, I'm just going to go back to Earth for 1 second because we know most about Earth's magnetosphere because we live here. Whether we want to or not in 2020 is another debate, but we're here and we need to know about our magnetosphere because we need to protect ourselves from space weather, which is just a way of describing the changing conditions on the sun, in the magnetosphere and in the upper atmosphere, otherwise known as the ionosphere of the Earth, which can have an impact on our technology. So to give you an idea of how important space weather, how well it's regarded by the community, here's just some of the spacecraft which are currently in orbit around the Earth and what we call upstream of the Earth, sampling the solar wind that's headed towards us, sampling the sun up close, for example, with Solar Orbiter, which we at DIAS have involvement in, and sampling the magnetosphere. So there are a huge amount of eyes on this problem. And that's, as I say, because of the technological havoc that space weather can wreak. So, for example, it can result in changes in atmospheric drag, which has impacts on our ability to accurately know the position of a spacecraft in low Earth orbit. It can have an impact on our navigation systems. And there has been, historical cases where aviation has been disrupted because we lose navigation, particularly close to the poles. It can result in scintillation of signals that are traveling through the ionosphere or the upper atmosphere. If you think about GPS, which you all rely on if you ever use Google Maps, other mapping tools are available. I don't work for Google. But GPS is worth something like, I think I read 1.4 trillion US dollars to the global economy. So if you have a load of scintillation going on, which is making your GPS unreliable, even a portion of the time, that has a huge economic impact. So understanding magnetospheres, it is critically important. And at Earth, we've got all these space-based eyes. We've also got lots of cameras on the ground, particularly in the high Arctic, to look at things like the aurora. So at Jupiter and Saturn, I'm really interested in understanding how we can study the physics of a magnetosphere in a different parameter space. Jupiter's magnetic field is so many times bigger than the Earth's. It's also, a huge planet that's rotating really, really rapidly. And so that introduces some interesting physics that we don't see at the Earth. And my research and that of my group focuses a lot on a process called magnetic reconnection, which is a process whereby, as you can see from this kind of mesmerizing GIF on the bottom left, magnetic field lines can sync together and merge together, and they meet and then they break. And in doing so, they form a new morphology of field lines. And that reconnection process happens in magnetospheres. It happens at the day side between the planetary field and the interplanetary field, which is associated with the sun. But it also happens on the night side. And my work and the work of many others has sought to estimate how much energy is transferred by reconnection events. And this is not a scientific unit, but an estimate of the energy that's released in a typical reconnection event at the Earth is about the energy it would take to boil 2.5 billion 1 liter kettles. I forgot to put the amount of water in the kettle for those who are on the more pedantic side, but a huge amount of energy being explosively released and transferred through this process of reconnection. That's what I'm really interested in studying at Jupiter and Saturn, because they're such huge systems and so dynamic. Okay, so the fourth thing that I want to focus on before I just talk about some future perspectives very briefly is planetary aurorae, which of course is linked to the physics of planetary magnetospheres. And so, you know, many of us have been lucky enough to observe Earth's aurora from the ground. Here's what it looks like from above. I mentioned already that Jupiter's aurorae are the strongest in the solar system, and you know, Saturn's aurorae are this is just a simply stunning image of the aurora in ultraviolet, but there are auroral emissions across different wavelengths, so in infrared, ultraviolet, and indeed X-ray in the case of Jupiter. Here is a movie which I just could not resist showing of, maybe some of you have seen some like this before, but just of what Earth's aurora looks like when you're in orbit above the Earth. And it really gives you the perspective on this so-called auroral curtain. So it really gives you a sense of the height of auroral emissions. And I think is a really good way to visualize that auroral emissions are caused by energetic particles traveling along magnetic field lines down into the polar regions. And so they have a height associated with them. And indeed, that is, of course, linked to the distinctive color of the emissions, depending on which particles are at different heights in the atmosphere. So, you know, absolutely stunning to observe. If none of you have, some of you haven't seen it, I would strongly encourage it. I saw my first aurora in Iceland many years ago, and it was just amazing. But yeah, Jupiter and Saturn are you know, spectacular places to look at the aurora. So here's just a schematic sketch. This was actually a press release that myself and colleagues put out a couple of years ago, where we were studying Jupiter's X-ray aurorae and their link to the solar wind. And so this was kind of to give you just a sense of all these particles just flooding down along these magnetic field lines and let me fix my pointer again, and causing this dynamic auroral display. For X-rays, we use space telescopes like Chandra or XMM, some of you might have heard of that, to study the X-rays. For ultraviolet, these are images which actually appeared on the cover of Nature magazine, taken by the Hubble Space Telescope, shown here on the bottom left, of Saturn's very dynamic aurora. That was a campaign back in 2004 when Cassini was on the way to the planet. But we can also look from the ground with infrared telescopes like NASA's IRTF facility in Hawaii. So we have multi-wavelength eyes on planetary aurorae. And this month, hot off the press, is one of the most exciting times to study planetary aurorae, because I know you talked about a conjunction between Saturn and Jupiter. Well, specifically, if you're a magnetospheres person like myself, Saturn is, it's moved out of the tail right now, but in sort of late October through November of this year, Saturn was situated in Jupiter's magnetotail. So if we look at this bottom figure here, this is Jupiter's magnetosphere, and I talked about the field lines on the night side, so the side that faces away from the sun, stretching to these huge distances behind the planet. And Jupiter is just so massive, and its magnetic field is so strong, and its magnetosphere is so gigantic, that its magnetotail stretches all the way to the orbit of Saturn. So, you know, more than 4 astronomical units behind the planet. And once every 19 years, Saturn and Jupiter are aligned such that Saturn is actually sitting in Jupiter's magnetotail. And this is an image or a sketch from the New Horizons flyby, where the New Horizons spacecraft went down Jupiter's magnetotail. So we have some idea from that campaign of what Jupiter's magnetotail is like. And so the geometry through, particularly through November, was so favorable to observe this. And so there have been a couple of targeted campaigns. So there was a big Hubble Space Telescope ultraviolet campaign led by a colleague of mine at the University of Leicester. And actually, if you Google him, he's already released some of the images publicly of what kind of aurora you get on Saturn when it's in another planet's magnetosphere. My PhD student in Southampton has led in an X-ray campaign with Chandra. And I asked him this afternoon if he had anything that I could share, and not yet is the answer, and we're working on it. But it's just such an amazing opportunity to understand how can you even produce an aurora when you don't have, a magnetosphere shaped by the solar wind, as is the kind of canonical picture like I'm showing you here. So when you have, a magnetosphere within a magnetosphere, that introduces some totally different physics and a completely different parameter space. And yeah, as I say, it's a once every 19 years opportunity. So actually, we missed the previous 19-year opportunity, but the time before that, Voyager had some measurements of Saturn and Jupiter's tail, but no auroral measurements. So we've had in situ measurements by a spacecraft of the plasma and the magnetic field, but we've never had, Hubble or Chandra observations. So we're sort of beyond excited to see how these results evolve. Okay, so I should stop soon, but I know I've talked a lot about the gas giants, but I just want to flag that, there are 2 other planets out there beyond Saturn that we have not visited with an orbiter, and we really need to go to both Uranus and Neptune to complete our picture and to complete our understanding of the solar system. And they are amazing worlds in their own right. They have a lot of unknowns about their interiors. They have really interesting atmospheres, particularly Neptune. It's a very, very windy place. From a magnetospheric point of view, they're absolutely fascinating. So Uranus is almost completely tilted on its side, such that its North Pole is in its middle. And we just don't know what happens to make it be that way, but it results in some incredible configurations of magnetic field. There are also rings, there's some really interesting moons, and yeah, questions about origins and relation to the formation of the solar system. So there's currently a lot of interest in going with a dedicated orbiter to one or both of these planets. And I'm cautiously optimistic that will happen before I retire. It's obviously going to take a long time to get there, but there is a launch window just in about the next decade for Uranus that would be fairly favorable. And there is significant community support, and a lot of papers recently were submitted to something called the Decadal Survey in the US to try to make the case to funders and science policymakers that these planets need to be explored to complete our picture of the solar system. But planets which are going to be explored again, or spacecraft which are planned, include ESA, European Space Agency, is sending the JUICE mission to the Jupiter system. That's got to focus on habitability. It's got to focus on moons. It's the Jupiter Icy Moons Explorer, JUICE. So that is going in the next couple of years, and it will get to Jupiter around the 2030s. Europa Clipper, I already mentioned, is a NASA mission which is going to fly to Europa and focus particularly on that moon and its prospects for a subsurface ocean. And that's at the well advanced stages. Actually, myself and others in my group are collaborating with some machine learning experts at the NASA Jet Propulsion Lab to look at the kind of software that we need to analyze data in a semi-automated way from Europa Clipper. So excited about that as well. And then one which is a cross between real life and sci-fi, but may go is Titan Dragonfly, to go to Saturn's moon Titan and sort of hover and explore that incredible moon. So I don't know when we're going to get another orbiter at Saturn like Cassini, but Jupiter is definitely a target for the next decade or so. And so I'll just end with this picture because I just love showing this picture every time I give a talk about these amazing worlds. And this is an image taken by the Cassini spacecraft. It was part of a public campaign where people were encouraged to go outside when they knew this picture was being taken and sort of wave at Saturn. So I was outside in my pajamas that evening, waving like a loon and scaring my neighbors. But this image, I think, is stunningly beautiful, but also just illustrates not just how far we've come in terms of our technological developments, but what is our place in the solar system. You can barely see us. We're a pixel across Earth and Moon. And just the vastness and beauty of complexity that there is in our solar system, but yet still within our technological reach. So lots that we found out, still lots to learn. I hope I've given you a flavor and maybe told you some things that you didn't already know. And I'm very happy to take any questions that you might have. So thank you very much.
Oh, thank you, Caitriona. That is a fascinating talk and overview of those big gas or ice giants. And I must say that picture you ended with, it is fabulous, and it is my favorite of all the close-up images from the Cassini and Galileo, those probes. I share your optimism too. We can't stay as a species stuck on one planet. We have to get out there.
Yeah.